Assalamualaikum and greeting to everyone. My name is Muhammad Tazri and on behalf of my group, I would like to present of our project title, Welding Temperature Sensor. So before we looking further, I would like to introduce our team member. So first Muhammad Fahmi bin Muhammad Hanif. Second myself Muhammad Tazri bin Rahman. Third is Muhammad Iman bin Abdul Halim. And fourth is Matan Morgan Ravindran. We offer the outdoor, let's begin. So next slide. Morgan, okay. So introduction. To start off, let me give a brief introduction to our project. So in many industrial environment, welding process generate extreme heat. If this heat is not properly monitored, it can lead to serious problem, such as structural defects, equipment failure, and safety hazard for worker. Therefore, our group proposed an IoT-based temperature monitoring system that continuously track thermal condition of welding process in real time. The goal is simple: to detect abnormal temperature before they cause damage and to alert the operator immediately. The approach shifts maintenance from being reactive, where we only respond after something breaks, to being predictive, where we identify problems early and prevent them altogether. Okay, next slide. Moving on the general overview of our system monitor three key parameters of the welding process. First, weld zone temperature, which help us detect any leak of blockage in the height zone. Second, heat affected zone temperature, which allow us to assess the cooling performance of that system. And third, cooling rate monitoring, which help detect mechanical wear over time. Or sensor data is transmitted to an Arduino Uno microcontroller. When any reading exceed the safe operating range, the system immediately active a warning LED to alert the operator. For this project, we simulate the entire system using Tinkercad, where function meter were used to replicate the behavior of real sensors. So next slide. So the objective. Now let us look at the objective of this project. We have three main objectives. First, to develop an IoT monitoring system using Arduino Uno that can track real-time thermal cycle throughout the welding process. Second, to detect abnormal automatically, such as sudden temperature spike or inconsistent in the cooling rate, so the system can respond without any manual intervention. And third, to demonstrate data analytics by using real-time data analysis and cloud notification to transform our maintenance approach into data-driven practice. So next slide is system overview. Okay, finally, let me walk you through the system overview, which describes how our system operates from start to finish. The process begins with initialization. The Arduino and its pins are set up and the temperature threshold defined. Next is sensor sampling. The system continuously reads the temperature value from the sensor. This is followed by data processing, where the analog signal is converted into a temperature reading in degrees Celsius and compared against the safe operating range. The system then enters the decision-making stage. If the temperature exceeds the limit, the condition is flagged as abnormal. Otherwise, it remains normal. Based on that decision, the output is displayed. The warning LED turn on for abnormal condition and remain off when everything is normal. The data is then sent through the IoT transmission stage, where readings are sent to a monitoring platform for remote access. Finally, the system enter a short delay before repeating the entire loop again, ensuring continuously real-time monitoring. Okay, that concludes my part. I would like now to pass it on our next presenter, who will take you through the component used in the system. Muhammad Fahmi, thank you.
Okay, thank you, Tazri. So today, I am Muhammad Fahmi Muhammad Hanif. I would like to continue the presentation for the components. The main components used in this project are Arduino Uno as the main controller, TMP36 temperature sensor to measure temperature, 16 times 2 LCD display for real-time reading, potentiometer and resistor, jump wires, breadboard, and Tinkercad for simulation. Next. For this, Arduino Uno function. The Arduino acts the brain of the system. They receive input from the temperature sensor, process the data, controls the LED indicator, and display the temperature value on the LCD screens. Next. For the potentiometers, the potentiometer function as a variable resistor. It adjusts the voltage level and send analog input to the Arduino, which is used the simulated temperature change in this project. For the resistor is limits the flow of electrical current in the circuit and the protects electronic component from the excessive current. Next. For the TMP36 temperature sensor, is a use to measure temperature. It converts temperature change into analog voltage signal, which can be read Arduino and converted into Celsius values. And then the LCD display. The LCD display provide an interface between the system and the user. It shows the current temperature value and the condition of the system, whether it's normal or abnormal. And breadboard is used to view and test the circuit without soldering. It allows easy connection of components and quick modifications. And then the jumper wire. Jumper wire are used to connect all components in the circuit and allow electrical signals to flow between them. For the system functionality, the real-time temperature sensor is used TMP36 analog sensor connected to Arduino to continuously measure voltage change and convert them into temperature values in Celsius. And then local visual telemetry LCD display utilize a 16 times 2 LCD provide real-time high contrast temperature readings on the site monitoring. Display calibration control used to 10K kilo potentiometer connected to LCD V0 pin to adjust display contrast according to industrial lighting condition. IoT edge communication, transmit and receive temperature data via Arduino UART TXRX to IoT modules, which is ESP8266 or ESP32 for cloud-based monitoring and data logging. And then lastly is the thermal safety safeguards. Compare temperatures reading with prevents threshold to identify normal critical condition and trigger real-time safety alert. Next. This is a diagram circuit. For the next part, I will give to the Morgan to explain about user interface system. Thank you.
Thank you, Fahmi. So next we'll jump to user interface system. The system interface is designed to be simple and user-friendly. 16 times 2 LCD is used to display the real-time temperature reading and system status, indicating whether the condition is normal or abnormal. In additional, an LED indicator provides visual feedbacks where the LED turns on when the temperature exceeds the safety thresholds and remains off under normal condition. For remote monitoring, an IoT dashboard is used to visualize live temperature data in real time. So this is our table input stage. TMP36 temperature sensor, continuous thermal voltage sampling, and the processing stage. Arduino Uno voltage to Celsius conversion, 1000 ms refresh loop, and telemetry stage, IoT cloud, gateway, data logging, dashboard, and TX and RX serial communication. And last one, output stage, local display system, 16 times 2 LCD, real-time temperature display, manual contrast control. So the data analysis, the test data for the 20 simulation samples are analyzed in the sector. In Tinkercad, 3 potentiometer were tuned to simulate various scenarios under the welding condition. A fault occurs when none of the monetary perimeter is outside of its limit of operation. In order to simplify, the three sensor reading are lumped together into a single health index based on the worst case maximum division parameters. So now we go to figure analysis. There's a few tables regarding temperature reading, period summary, and temperature reading. So there's a few tables and the temperature data summaries, summary statistics, parameter, maximum parameter, value, remarks, high record, the reading count by conditional, normal count 10, percentage 30.33, description less than 30% Celsius. I then next to the Tinker simulation, you can see a increase time second, the high, and decrease to 28 derajat Celsius. So the descriptive, the analysis cover the industrial data collected during the 145-second simulation of the TMP36 temperature sensor, which clearly outline for distance operational phases. The system begins in an international baseline state, bracket 0 to 26 seconds, at a normal temperature of 26.5 Celsius, and climb steadily within a safe green zone under 30 degree Celsius. It went transition into a warning phase, 30 to 35 seconds, 30 to 55 seconds, at the temperature crosses the 30 Celsius. Threshold at the 30 seconds mark, bracket 30.1 Celsius, triggering a yellow bar warning state during its underwards tragedy. The situation inserted into a critical phase 60 to 95 seconds at the 60-second mark, where the system breached the high temperature thresholds of 33 Celsius at 33.1 Celsius and ultimately reached the peak temperature of 34.2 Celsius at 80 seconds, maintaining the critical stage for a total duration of 40 seconds. Finally, during the cooling phase, 100 to 145 seconds, the temperature begins to drop after 90 seconds. moving back down through the warning zone before successfully returning to the normal zone at 130 seconds, bracket 29.5 Celsius, and concluding the simulation at the stable 28.0 Celsius. Then we move to predictive. Based on the visual train and patterns within the data, feature system behavior under similar operation condition can be effectively progressed through three key insights. First, the graph display distinct clinical behavior characterized by a clear bell-shaped thermal curve. This suggests that if the system utilizes the automotive heating element or operate in an environment subject to periodic heat peak, the temperature can be predicted to the cycle back upward after heating baseline room temperature of an approximately 25 Celsius to 26 Celsius. Second, the time to critical estimate revealed that when the system start heating from this 26 Celsius baseline is requirement approximately 60 seconds of continuous operation to breach the critical safety thresholds of over 33 Celsius. Finally, the analysis highlight a noticeable system lag where the peak temperature occur at the 80 seconds mark but takes about 50 seconds of cooling time to return the system to a safe normal status at 130 seconds. This indicates a thermal depreciation lag, meaning the system retain high internal heat for a prolonged period even after the cooling mechanism have likely been activated. So next I pass to Iman. Thank you. Right. Iman. Iman. It's okay, I continue the next slide. So hardware and system and adjustment. Introduce active cooling because the temperature span a prolonged period 40 seconds in the critical red zone. The setup need activate cooling mechanism like a DC fan or cooling heat sink triggered the moment at the warning thresholds is breached. Second, calibrate sensor placement. Placement ensure the TMC is not placed too close to high heat component, likely an overwork microprocessor or edge bridge motor driver to avoid calculation false. Iman, Iman ada tak? Saya continue sampai dia masuk, lepas tu disambung lah.
Yeah, continue.
Okay, next 3.0 signification of the proposed system, industrial impact and benefit, enhance welding quality, prevent critical structural defect like cracking or incomplete fusion by maintaining optimal temperature, minimize material waste, reduce costly rework and material rejection through early anomaly detection, improve operator safety, provide real-time hazard warning to protect worker from extreme thermal risk. Lastly, boost productivity, allow immediate operation adjustment, significantly reducing machine downtime. So 3.2 main implementation challenge. Sensor calibration demands high precise calibration to ensure accurate reading under extreme welding heat, harsh environment. Device must withstand physical wear, instant spark, smoke, and electromagnetic interference EMI. Signal stability, wireless data transmission can face connectivity interruption due to thick metal, sectional, and heavy machinery. Machinery development cost requirement upgrade is still for hardware component and cloud setup. The next
Then I
business.
think the next slide boleh bagi dekat Iman lah.
Okay. Atau saya nak habiskan yang ni atau bagi yang next tu bagi kat dia.
Boleh juga.
Okay, last slide. Future and business and future opportunities. Target markets ideal for automotive assembly lines, heavy fabrication industrial and technical training institution. Commercialization potential can be marketed as portable monitoring kits or indicated cloud subscription service. Future roadmap highly scalable through the integration of big data and analytics, custom mobile apps, and artificial intelligence AI. Lastly, predictive maintenance ready to transition from time-based servicing to AI-driven predictive failure analysis in Industry 4.0. So next, I pass to Iman.
Thank you for Morgan. I will continue. The next slide is conclusion. The conclusion is the successful development and simulation of this IoT-based welding temperature monitoring system demonstrate the profound condition of integrating microcontroller and smart sensor into advanced manufacturing network by continuously supplement thermal profile with the TMP36 sensor and providing instantaneous telemetry via an LCD interface. The framework effectively leverages industry data by accurately mapping operational state through the descriptive analytic, predicting thermal failure through trend identification and recommending immediate corrective action. Via predictive algorithm, ultimately this implementation bright fundamental concept of industry information technology such as sensor calibration data, drive decision making and edge processing to directly enhance workshop safety, minimize material waste, and optimize overall productive moving forward. The project lay as scalable foundation for Industry 4.0 application with promising feature roadmap that include cloud telemetry integration, mobile device compatibility, and AI-driven predictive maintenance strategy. Next slide.
This is our reference to you guys that my team do follow the references. Next slide. Okay, this is the coding we use for the welding temperature sensor. Next. This is the final project we have done. Thank you.